Hi guys, happy Thursday. I thought what I'd do today, since I don't have people in my multivariable calculus recitation, is go through the quiz and just do the quiz question by question. I know you guys have access in Gradescope to a key, but sometimes it's nice to see the process. Also, U substitution is one of the hardest topics, I think, personally, in single variable calculus. Requires not only skill with derivatives and antiderivatives, but a sense of the big picture. And I guess what I was going to say is you only develop that through practice. So for this section in particular, thinking forward to the final, try and get as much practice in as you can. You also have to be willing to try and fail. That's the other thing. Some people don't like that. They want to know exactly how to do the problem from the beginning. And when you start out, you might make the wrong choice for some of your U substitutions. That's okay. That's par for the course. So let's take a look at the quiz problems here. Okay, so problem one, oops, I guess we have an integral too, right? So indefinite integral of 9x squared times the quantity x cubed plus 1 all squared. And in U substitution integration, what we're looking for in every single problem, no matter what the function is, we are looking for evidence of the chain rule, right? So remember what the chain rule says. Chain rule says if we take dx of some composite function, so some function within another function, f of g of x. Well, that will equal f prime of g of x times g prime of x. So that's differentiation using the chain rule. When we do integration by U substitution, all we're doing is trying to run that backwards. We're saying, can we find a function and its derivative hiding somewhere inside the integral and run this process backwards? So that's kind of by summary what we're going to do. Let's take a look at this problem here. So the first thing I notice here is I have some x cubed, so I have x cubed plus 1. That whole thing's being squared. That could be a good choice for my function u. And by the way, when I wrote that out with f of x and g of x, right, that's the same as, g of x is the same as u. But instead of writing function notation, we're just going to use a single letter to represent that function. So x cubed plus 1, that might be a good choice for u. The reason I'm drawn to that is that I see I have the third power of x right inside here. Now the second power of x outside here. So maybe this is that function, that inside function g of x, and maybe this is g prime of x, right? So this is where I have to actually try something. For this problem, you could actually do, there's more than one choice that you can make for u. If you choose u equals x cubed, the problem will be fine. If you choose u equals x cubed plus 1, the problem will also turn out fine. So don't get hung up in this beginning phase of like worrying that you're not doing it right. Let's just pick something for you. Okay, so let's say u equals, oh, that's not really showing up very well. Let's switch colors. So we'll try u equals x cubed plus 1. Okay, so this is our choice. So we might even say like let u equal x cubed plus 1. We're inventing this variable to help us with this problem. We don't know what this antiderivative is. It's just too complicated to see what's going on there. But maybe if we let that x cubed plus 1 just be a single letter, we might be able to discover some structure in the problem here. Okay, so based on my choice of u being x cubed plus 1, I'm now going to take the derivative of this equation. And I'm going to show it one way, your instructor might show it another way, you might find another video that does it slightly different. They're all going to end up with the exact same thing at the end, so don't worry if you've been shown a slightly different way. Okay, so on the left-hand side, the derivative of u we write as du dx, right? So we're differentiating with respect to x on both sides. The derivative of x cubed with respect to x is 3x squared. Now, what we do, because we have this differential here, right, that's actually important in our integral. It tells us with respect to which variable we're integrating. What I'm going to do with this du dx equals 3x squared is I'm going to multiply both sides by dx as if this were a fraction here. And when I do that, I get du equals 3x squared dx. Okay? So this was my choice. I chose u. And based on my choice of u, I found this du. And what I'm trying to do is replace all the x's and all the dx with u's. And if I picked a good thing for u, it will also give me an integral that's a lot easier to solve. So let's see, if I did that, well, that's u, right? So I'd have u squared, right? If I rewrote this in terms of u, that part right there would be u squared. And then I need a du somehow. What I'm hoping is I can just substitute, like I'll have exactly du here. Well, I don't have exactly du. I have 9x squared dx. That's the part I haven't figured out how to deal with yet. And so if I look down here, I do know that du equals 3x squared dx, and I have 9x squared dx. So what I can do with my equation here is multiply both sides by 3. So 3 du equals 9x squared dx. That's exactly what I have up here, so 9x squared dx. So since I've now figured out a way to substitute out all my x's, I can rewrite this integral strictly in terms of u. So I have the integral of, let's see, there's u squared, right? That's my u squared right there. And then the 9x squared dx altogether, that constitutes 3 du. So times 3 du. And that's a way easier antiderivative to do, right? It's just the power of u. We're going to bump it up by 1 and divide by that new power. Okay, so what do? I'm going to factor that 3 out. So we have 3 times the integral of u squared du. Notice that if I haven't taken my antiderivative yet, I still have the integral, and I still have the differential here, the dx or the du. This should stay with me all the way up until when I take my antiderivative, which I'm just about to do. Okay, so time for an antiderivative. Power of u is going to go from 2 to 3, and then we need a 1/3, right, to cancel when that u comes out in front. So 3 times 1/3 times u cubed plus c, right? Super important. We want to see that at this step. We don't want to see you put a c at the very end of the problem, just like slap a c on it. We want to see that as soon as you've done your integral. Notice too that I've stated that all these things are equal, right? It shouldn't read like a sequence of steps. I know like some of the solvers just have like 8 or 10 or 12 just like steps, but they don't really show the relationship between these things. Okay, so I'm almost done. 3 times 1/3 is 1, so really what I have is just u cubed plus c. And remember at the beginning I said I'm inventing u, right? U isn't a variable I'm just inventing to help me with the problem. So at the end of the problem, I'm going to change my u's back to x cubed plus 3. So I have x cubed plus 3, or sorry, plus 1, that's u, raised to the 3rd power plus c. And my problem is done. Okay, so if this is something that you struggle with, especially if you're not sure if you're picking the right u, what you should do at the end of the problem is check it by taking the derivative, right? Integrals and derivatives are inverses. So if this is the right answer, if I take d dx, I should get 9x squared times x cubed plus 1, the quantity squared. So let's see what happens when I do that. So d dx of the quantity x cubed plus 1 cubed plus c. Okay. Well, so here's a composite function. The inside function is x cubed plus 1. Oh, sorry, that's to the, yeah, that's right, to the 3rd power. Okay, so what we're going to do is take that function, drop it down from the 3rd power to the 2nd power, and pull that 3 out in front. So we'd have 3 times x cubed plus 1 to the 2nd power. And now by the chain rule, we need to multiply by the derivative of the inside function, which is 3x squared. And if I look at what I have here, 3x squared times 3 is 9x squared. And there's my x cubed plus 1, the quantity squared. So I finished my problem. Okay, moving on to problem 2 on quiz 6.2. Here we have the integral of 5x squared over x cubed minus 3 times dx. And again, you know that you need to use u substitution because of the section that we're working on, but if we didn't, we could just look at this and say, okay, that's not like a common derivative, right? I don't know what function this would be the derivative of, right? So if we see anything that's more than just like a power of x or a known derivative, like natural log, e to the x, something like that, we should be thinking u substitution. U substitution is just a tool to keep us organized, right? If you think back to the problems that I did earlier in the semester using a combination of derivative rules like quotient rule and chain rule, I would often invent variables to just take the place of a complicated function so that I didn't have to write the whole thing out. And so I could try and see some structure in the problem. Then I can assemble it at the very end, right? So we're doing the same thing here with these u substitution problems. So I'm looking again for a function and its derivative. I see the 3rd power of x in the denominator. I see the 2nd power of x in the numerator. I'm going to take the higher of those two, especially if they just differ by 1. I'm going to take x cubed or x cubed plus 3. When in doubt, I would say take the larger of the two options, right? If there's like more terms, if there's a constant here, include that constant. Will probably make your life a little bit easier. So let's let u equal x cubed minus 3. right? My thinking being the derivative of a third degree polynomial is going to be some sort of second degree polynomial. Maybe it's 5x squared, or maybe I can turn 5x squared into what we're looking for. Sorry, it's a little bit small. It's x cubed minus 3. Okay, so if u equals x cubed minus 3, then du dx equals 3x squared minus 0, right? Because the derivative of 3 is 0. And now I can separate this into its differential form, du equals 3x squared dx. Okay, this is like once you've picked u and found du, we zoom out for a minute. We don't get lost in the details of doing the math. We look back at the original problem and say, okay, do I have these things? All right, there's a u, right? So I'd have a u in the denominator. And I wish I had 3x squared dx up top. That's what I really wish that we had, right? If we had 5x squared dx, I could just change that into a u, and I'd have the integral of du over u. And that's an antiderivative that we know. So what can I do here? Well, 5x squared dx is what we want. 3x squared dx is what we have. If I take this equation and I divide both sides by 3, I have du over 3 equals 1x squared dx. Okay, that's better, right? We wanted 5, we had 3, now we have 1, but what we can do now is multiply both sides by 5, and then I'll have 5x squared dx. I'll have exactly what I want for my equation up here. So multiplying both sides by 5, I have 5 multiplied by 5 divided by 3, so 5/3 du equals 5x squared dx. Okay, so again, a recap. I picked u. U told me what du had to be. I don't have choice over that once I've picked u. So I figured out what du needs to be. I need to get a du into that integral if I'm going to integrate with respect to u. Okay, so what can I swap out for du? I need a 3x squared dx. Okay, well, I don't have that. I have 5x squared dx. I don't want to split that up using addition or anything like that. That's going to get too messy. Can I multiply by some number and get exactly that? Yes, I can. Divided by 3 to give it 1x squared dx, and then multiply by 5 to make it 5x squared dx, which is exactly what I have there. Okay, so now it's time to rewrite my integral. My original integral in terms of x was too complicated. I invented u to help me here. And so my new integral is the integral. Well, let's see. We have u in the denominator, right? So we have a u down there. That's that x cubed minus 3. And what else do I have? I have a 5/3 du. Now, where I put this is kind of up to me. We know that there's a constant multiple rule for integrals. So multiplying by 5/3, I might as well just stick that on the outside of the integral and deal with that later. So I have 5/3 times du. And now look at how that choice of u changed this from a challenging problem into a really easy one. Du over u is a known derivative. We know where that comes from. It was in one of the last sections that we did before switching over to integrals, where we studied exponential and logarithmic functions. We know that the natural log function, natural log x, its derivative is 1 over x. Natural log u is 1 over u du. So it's time to take an antiderivative. So we have 5/3 times the natural log of u. Now, when we do this antiderivative of 1 over u, we should, it's good practice, put absolute value bars around the argument to the natural log. So it's not a super important detail here, but we know that the natural log function can only take positive inputs. So if we throw those absolute value bars on it, we'll be in good shape. Okay, so 5/3 times the antiderivative of 1 over u du, which is natural log u, and plus c. Remember that plus c occurs as soon as we've taken an antiderivative. Last step then, we're going to change that u back to whatever it was in terms of x, so x cubed minus 3. And our final answer is 5/3 times the natural log, absolute value, x cubed minus 3 plus c. Okay. So, a little bit of a shorter problem. I want to highlight some ways that you can get 3 out of 4 points on an exam if you are working on a problem like this. Okay, number 1 way to get 3 out of 4. No plus c. All right, plus c, that's the easiest way to get, to score well on these problems. I had a student last semester who had a note card, and half of the note card was just plus c, a giant plus c, so that they didn't forget that. It's an important detail because these antiderivatives are whole families of functions, not just a single function. Okay, so no C, that's one way to mess these problems up. How else can we do that? Oh, if we don't switch back to X. This is all bad. Okay, so no plus C, we don't switch back to X. Let's see, what else could we do to mess this up? Oh, if we don't state U or du, that's really bad. It's difficult for us to understand what you did there. So even if it's a problem where you think it's so easy, it's like really anyone can see what U and du is, state it explicitly, right? U equals and write du equals. That way we know you understand these problems fully. Okay, so make sure you do that, U and du. Those are those are definitely the main ones here. I guess yeah, I'll leave it at that. All right, on to problem 3. So I talked through a lot of those problems. I probably talked more than you want me to. For the rest of the problems, I'm going to go a little bit faster. I've sort of said my piece about the plus C's and the details. So just jump right into this. So I have 4x to the 4th plus 2, and I have an x cubed up top. So 4x to the 4th plus 2 is probably going to be a good choice for you. So I'll let u equal 4x to the 4th plus 2. And then du dx. Derivative would be, let's see, so 4 comes out, we get 16 x cubed plus 0. And so if I separate this, I have du equals 16 x cubed dx. Okay, so what do I have? I have a u squared in the bottom. That's fine. I can take antiderivatives of negative powers. And then I don't quite have du up here. I want 16 x cubed dx, and I just have 1 x cubed dx. This problem, I'm going to show you another trick. Some people like this, some people don't. If you don't like it, just use the same method we did on the other problems. If I want a 16x cubed, here's how I can make a 16x cubed appear in the problem without changing it fundamentally. We have a constant multiple rule, so if I multiply by 16 and divide by 16, we know that that's not going to do anything, right? Multiplying by 16 and dividing by 16, those are inverses. But by multiplying by 16 on the inside of the integral, and multiplying by 1/16 on the outside of the integral, I've changed the inside of the integral to exactly what I want, right? So instead of like manipulating du into what I have in the integral, I'm now manipulating the integral into what I have for du, right? So very similar process here. Some people like it, kind of hacking the integral. The important thing is if we're going to multiply by 16 on the inside of the integral, we have to divide by 16 on the outside. Okay, so if we do that, what do we have? We have 1/16, forgot that already, times the integral of, okay, so 16x cubed dx is du. So I have du over, okay, well that's u, and it's u to the 2nd power, so u squared. And we know powers of x, powers of u. We're going to just write that as a negative power, so we have 1/16 times the integral of u to the negative 2nd du. And so to integrate, just like we do for positive powers, we're going to add 1 to that power. So we have 1/16 times u to the negative 1st power. And then we're going to divide by that new power, right? So we will divide by -1. Divided by -1 just changes the sign from positive to negative. So negative 1/16 u to the negative 1st power plus c. And last step, we'll change it back in terms of x. So negative 1/16 times u, which is 4x to the 4th plus 2, to the negative 1st power, plus c. You may also see this written as a fraction, so you might also see it like this, negative 1 over 16 times 4x to the 4th plus 2. Right, that's the same as the negative 1st power. Either one of these are both fine. Perfect. Okay, problem 4. Integral of 4x plus 4 times the quantity x squared plus 2x cubed. Again, I'm going to take my higher power of x, so x squared, and really I'm going to take x squared plus 2x, right? We need a function and its derivative being multiplied together, right? That's what the chain rule generates. So let's let u equal x squared plus 2x, and then du dx equals 2x plus 2, and du, just du by itself, equals 2x plus 2 times dx. Okay, so this is where I pause. I'm going to look for these pieces in my original integral, see if I can rewrite it using u. Okay, so what do I have? Okay, that's a u to the third power, right? So u cubed. And then what's left over is 4x plus 4 times dx. That's not exactly what I have. So in this moment, sometimes you'll have problems where it just works. You just get du without any extra work. In most problems, though, most u substitution problems, we have to mess around with the coefficients at least a little bit to make this work. So what do we want? We want 4x plus 4 times dx. We have 2x plus 2 dx. Aha, if I take 2x plus 2 and multiply it by 2, I'll get 4x plus 4 times dx. So let me do that down here. Multiply both sides by 2. I have 2 du equals 2 times 2x plus 2 dx. And so 2 du is the same as 4x plus 4 times dx. All right, so that's my pre-work finding u. So I chose u. Du came from my choice. Now I'm going to rewrite my integral in terms of u. So what do I have? I have a u cubed. And then this 4x plus 4 times dx, that's equal to 2 du. So u cubed times 2 du. By constant multiple rule, I can factor out that 2 outside the integral. Power of u, we're going to increase that by 1. So 2 times u to the 4th power, and then multiply by 1 over that new power. So 1 over 4 plus c, right? Du goes away, integral goes away, c enters. Okay, I can simplify 2 times 1/4, that's 2 quarters, or 1/2, as the kids say. U to the 4th, I'm going to change back into x's, so I have x squared plus 2x to the 4th power plus c. My problem's done. Okay, I thought one more thing I wanted to talk about for this problem 4. So we have this x squared plus 2x to the 3rd power, and we definitely know we can't just slap a 3rd power on these two. Exponents don't distribute like that. But we might be tempted to multiply this out. Unless it's really, really simple algebra, don't do that. This is what u substitution is for. It's problems just like this. So you do not want to get into expanding some big binomial to the 3rd or the 4th power. Just leave it as it is and use chain rule. Unless it's like a really easy power, like something being squared and you can use FOIL, it's going to be a lot easier to use u substitution than anything else. I know some folks got into a little bit of trouble with that on the quiz. Okay, here's problem 5, a little bit of a curveball here. We have natural log of 5x over x dx, right? So just like all these problems, we're looking for a function and its derivative. So we should consider 2 things. We have 5x in the denominator, so really 1 over 5x. We also have ln 5x. So is there a derivative relationship there? Well, the derivative of 5x is just 5, right? And the derivative of 1 over 5x, okay, so we use chain rule. We would like increase that by 1. Yeah, that'd be a little tricky maybe. We know that the derivative of natural log, though, right? That is a known derivative. The derivative of natural log is 1 over x, right? Ln x is 1 over x. The derivative of ln u is 1 over u. And what I see in the structure of this problem here is I see the natural log of something, that something being 5x, and I see that we have 1 over 5x. So this problem to me looks like we may be able to solve it without adjusting coefficients at all. Maybe we'll have to do it, maybe we won't. Let's try. So if we let u equal 5x, right? So u equals 5x. All right, what does that do for us? So du dx then would be 5. Is that what we want? Maybe. I don't really see a 5. Well, you know what? Let's try it anyway. Let's see where this leaves us. So if u equals 5x and du dx equals 5, then du equals 5 dx, or equivalently, since we only have 1 dx here, we would have dx equals du over 5. Okay, so this would allow me to get rid of my 5x's and my dx, change everything to u's. And one thing that we don't want to do, really, if possible, is write an integral that has both x's and u's in it at the same time. We're trying to sort of engineer this so they all switch over at the same point. What would that give us? Okay, so natural log of u, so we'd have ln u over u, okay, times dx, and dx is du over 5. So I'm gonna make a little bit of room here. I'm gonna put my du inside the integral and my 1 over 5 outside the integral. All right, anytime I have a constant multiple, I'm gonna typically do that. Let's fix this here, give us a little room. Okay, so now we say, all right, has this helped us, right? Is this an antiderivative that we know? Well, maybe, maybe not. There's a time when we maybe have to do this process more than once. So ln u over u du, man, I don't know. Well, we can repeat this process again. We probably shouldn't use the variable u again, so let me try this with v. Let's see if we can define some variable v that makes this a little bit nicer here. Okay, well, if v is natural log u, we know that the derivative of the natural log function is 1 over u, and that's exactly what I have here. So if v equals ln u, then dv du would be 1 over u, and dv then would just be du over u. Okay, well, let's see what we have here. Here's my ln u, right? So that would be v. This over a little bit. Switch colors too. So 1/5 times the integral. ln u is now just v. And I have 1 over u du. Well, 1 over u du is the same as just dv. Now that's an easy antiderivative, right? Just a single variable. So let's unpackage it then. So my antiderivative then would be 1/5 times v squared over 2, right? We're increasing that power of v by 1, plus c, right? So just v to the first power goes to v to the second power, divided by 2, we have a 1/5 on the outside. So 1/5 v squared over 2 plus c, or simplified, that would be 1/10 v squared plus c. So now let's unpackage this. Let's get it back in terms of x. Well, what was v? V was, well, we made v ln u. So this is 1/10 natural log u squared plus c, right? 1/10 v squared plus c is 1/10 natural log u squared plus c. Okay, now I'm going to go back to the original form in terms of x. I'm making it a little bit messy here. You probably will be more organized in your problem. You know what? I'll write it where it needs to go. It's right under here. So 1/10 natural log u squared plus c. Okay, I still have it in terms of x, but what's u? Okay, u is 5x. So my final answer then is 1/10 times the natural log of 5x squared plus c. My problem's done. So I did 2 rounds of u substitution here. This is one way to do it. If you pick the right u, you might be able to do this in one single step, right? If you pick u equals natural log 5x, the derivative of natural log 5x is going to be 5 times 1 over 5x. So, depending on your choice of u, this could be a single substitution or multiple substitution problem. The important thing is things are getting better as I go along. They're getting simpler and they're getting closer to a known antiderivative. Okay, last problem, number 6. Maybe the hardest one. It depends on your perspective. So this one, we have 2x squared times the quantity e to the 5x cubed dx. Okay, well, so we're looking for a function and its derivative. we know that the derivative of some power of x is going to be itself maybe times something else. So looking at like e to the 5x cubed, here are some possibilities. Each one of these will actually work. So could u be e to the 5x cubed? Could that be it? Or could u be just 5x cubed? Would that work? So it turns out that also works, right? Either one of these will get us to the right answer. I'm going to choose u equals 5x cubed. So I'm going to choose it to be that exponent there because I know the derivative of e to the u, right? That turns this into a problem that's pretty standard for us. So let's try that. U equals 5x cubed. Okay, well then du dx equals 15x squared. If I separate this by multiplying both sides by dx, I get du equals 15x squared dx. Okay, do I have that? Do I have these things? Well, I have 5x cubed, so that would be e to the u. And I have 2x squared dx. I want 15x squared dx, so how do I turn a 15 into a 2? Well, if I divide it by 15, I'd have 1. And if I multiply that by 2, I'd have 2. Right? So if I divide by 15, multiply by 2, I'd get what I want. So dividing by 15, and then multiplying by 2. So we'll have 2/15 du equals 15s cancel. Right? So multiplying both sides by 2, we get a 2 over here, 2x squared dx. Okay, so we changed our 15x squared dx, which we got as a result of our choice of u, and we multiplied both sides by 2, divided by 15, so that it matched our integral here. So we have e to the u, that's gotten rid of the x's here. We have 2x squared dx, which is the same as 2/15 du. And so our integral then, rewritten, 2x squared dx, that's our du, and we have e to the u du times 2/15. Right? So we're 2/15 du, and we have our e to the u. Okay, so time to take our antiderivative. We have 2/15. Antiderivative of e to the u is e to the u. So 2/15 e to the u plus c. And to finish the problem, we'll change that u back into our original substitution here, so 5x cubed. And again, you can check this by taking the derivative, remembering to use the chain rule.